So, in this module, as I promised earlier, we will be talking about dislocations and particularly screw dislocations. Again, screw dislocations are something very interesting in a BCC system. So, here we will look at the dislocation core of screw dislocations. Now, this is a BCC system and the rows that you lines that you see are along 111 direction. So, in a screw dislocation for a BCC, we all know that we should have Berger vector as well as line vector should be along 111 direction. And if we take this as the center or the origin, so this then we will have these lines representing the 111 directions. So, these are all representing 111 directions. Now, if you were to look at along any of these 111 direction, so let us say you are looking at a 111 along, so I am extending this, and let us say your so as if a person is looking towards the 111 direction. So, this is a 111 plane, meaning we have plane like this. Now, when you have something like this, you would see certain rows. So, all the atoms would lie in rows like this, and the rows can be actually designated as 3 different kinds. So, we have designated it here as A, B and C. Now, in each of the row the characteristics is same. Each of this row the atom spacing is apart by A by 2 111. Okay. But what is different between A, B and C, and what is common between C, C, C or B, B, B is that the atoms in this in these layers are in the same plane. And how much are they different? So, if you go from A to B, then it will be 1/3 of this Berger vector. So, this we know this is Berger vector. So, A to B, the difference between the atoms along this direction, along the 111 direction, you have a spacing of equal to A by 6 111. Similarly, when you go from B to C, and similarly when you go from C to A. But when you look at B atoms, all the B atoms are in the same plane. When you look at C atoms, all the C atoms are in one plane, and when you look at A atoms, then all the atoms, here we have only shown one row of A atom, but there will be other, for example, here will be one A, there will be another A, and those atoms will be in the same row. Now, here again it is we have tried to show the same thing in this BCC. So, here you have 4 cells in adjacent to each other, and here what you are looking, if this is the B row, this will become the C row, and you can see the, if you are looking from 111 direction, then this plane and this atom would be in the same plane, and so on. And if you are talking about A row, so all these atoms are here, the A row, and this will form A, this will be A row, this will be A row, this will be A row, and so on. So, what we are trying to say is that when you are looking in the 111 direction, there are 3 different kinds of rows. A, B and C, and we have described what is the difference, that the difference, the similarity first is that the Berger vector on along this is the same, which is A B by 2 111, and therefore, the atoms spacing is equal to A by 2 111, that is the shortest lattice vector. But when we go from the plane A to plane B, the atoms are displaced by this much amount, which is 1 by 3 of Berger vector equal to A by 6 1 1 1. Similarly, B to C, there will be a displacement of B by 3 equal to A by 6 1 1 1, and so on. Because of this, what you would see here is that now you have A, B and C. So, let us say A is the layer where you have the lowest level of atom, next 1 by 3 B, this is another 1 by 3 B, and then again another 1 by 3 B, you come back to A. So, what this is forming is a helical structure. Similarly, if you look at this one, this is forming also a helical structure only in the opposite direction. So, this was in the clockwise direction, which is shown in green. So, this is clockwise, this is clockwise, A, B and C, A, B and C, this is clockwise, and this maroon one are in the anti-clockwise direction. So, A, B and C, A, B and C. Now, this leads to what are called as hard core and soft core for the screw dislocations. Let us try to understand what are hard cores and soft cores. So, we talked about triangles over here. So, here we talked about triangles A, B and C. So, let us look at one of the triangles where the rotation of the atoms is clockwise. Now, let us try to draw it in a 3 dimension. So, how would it look like? So, let me try draw it from a little bit bottom. So, this is one row of atom, this is another row of atom, this is another row of atom, and this is A layer, this is B layer, this is C. So, let us say the atom is over here, and here it will be 1/3 shifted in the along the 1 1 1 direction. So, you remember this is okay, we will draw it again. So, this is B, this is C and again this is A. So, this was also A, and like I said from the previous slide, what should be this distance? This is equal to Berger vector, which is equal to A by 2 1 1 1. This is what we talked about. This Berger vector should be equal to A by 2 1 1 1 spacing of atoms in each row. So, this is A row and here the atom spacing is A by 2 1 1 1. But when we look from with respect to this plane, the difference between the atoms in this layer and this layer is 1 by 3 B, which is equal to A by 6 1 1 1, and this is again A by 1 by 3 B. So, this total becomes 2 by 3 B, and overall what you get is a clockwise structure like this. So, this is a, you can say, inherent screw, not dislocation, but inherent screw in BCC. Now, let us say that another screw dislocation with clockwise orientation tries to add with it. So, there is another screw dislocation, and over there the structure would be very similar. You will have so everything is similar, and here also this is clockwise, and what we get. So, now let us look at this one first. Here this is 1 by 3 B, this is also 1 by 3 B. So, the displacement in this direction is 1 by 3, this displacement in this direction is 1 by 3. So, the displacement in the B row will now become 2 by 3 B. So, this will be now somewhere over here. Over here the displacement was 2 by 3, here the displacement was 2 by 3 B. So, it becomes 4 by 3 B, which is equivalent to saying equal to 1 by 3 B. So, this will become 1 by 3 B, and this is B and this is B 2B. So, it is equal to saying 0. So, it remains at its position, relative positions. We are talking about the relative displacement of atoms when there is an inherent screw and there is an actual screw dislocation coming in and adding on to it. So, how the displacement looks like. So, now what happens here? Now, you see this is 0, this is 1 by 3B, this is 2 by 3B and there will be a, okay, let me first write it. So, this is equal to 1B and therefore, what we get is a screw dislocation possible, still a screw dislocation. And what is more important, so let me write down first here, this is a screw dislocation. What is more important here is that the relative positions of A, B, C remains same, meaning A and B layer are still 1 by 3B apart, A and C are still 1 by 3B apart. So, the relative positions and A of A, B, C remains same. And what does that mean? It implies that the energy of this core would be lower and therefore, this can be termed as soft core. Now, let us look at another possibility. Again we will start from an inherent screw. So, we will have to redraw this structure. So, we have A here, there is another A, this is B and this is C. So, we are only considering the clockwise triangle in the BCC. The other thing also you can take and you will see that you will get similar result, not similar, in fact, the same thing in the inverse order. Now, here we are adding, but this time instead of changing the inherent screw in the BCC, we will change the screw dislocation. So, earlier we the screw dislocation that we added was a clockwise. Now, what we will do is we will add a anti-clockwise screw dislocation. So, let A be at the same place, because we are talking about relative position, it will not make a difference. So, we will take a so over here we will put this here. So, this is so, here you can see this is a clockwise, okay, I will have to draw it over here. So, this was also clockwise and we ended with the anti-clockwise. Here we start with clockwise and adding a dislocation which is anti-clockwise, and then what we want to see what happens. So, first let me so these are the 3 rows. Now, let us look at it. We will start with B. So, over here this B is at 1 by 3 and here it is at 2 by 3B. Here this is 2 by 3B and this is 1 by 3B, B being the small b being the Berger vector, and this is the whole thing is the B, the Berger vector. So, if we add 1 by 3B to 2 by 3B, what do we get? We get 1 full B. So, the next layer, there is one layer here, this another layer is over here. We add 1 by 3B to 2 by 3B, we get one layer here, one layer over here. So, this is B, this is B, and A is relative. So, we keep A at the same place. Now, what do we get? We get a configuration which is very funny, in fact. This is like this and this is like this. So, what is happening? A, B and C, the layers which were supposed to be 1 by 3 plane apart, have now all been pancaked onto one plane. So, this is the, so what we are saying is that the relative positions have changed, implies this is a hard core. So, this is what we mean by soft core and hard core. Here soft core meaning that this is, so you have the inherent screw dislocation and a screw dislocation added when they are of the same sign, and you get a structure which is anti-clockwise, but what is maintained is the relative spacing between the different layers. So, they are still maintained and therefore, you can expect it to be lower energy. On the other hand, when you have a clockwise inherent screw in the BCC adding to an anti-clockwise screw dislocation, we get a structure where A, B, C layers get pancaked and there is no, the relative positioning of the atoms has been messed up. So, this energy will be much higher and therefore, this is termed as hard core, and this dislocation would not like to be in this. Now, instead of taking the clockwise screw inherent structure, we could have as well taken an anti-clockwise and then we could have done the same thing. So, what you would have found that anti-clockwise likes to go with anti-clockwise screw dislocation, but the anti-clockwise inherent structure does not want to go with clockwise dislocation, meaning opposite signs are not appreciated, they do not want to go together, they end up creating a hard core. So, this is the message that the same type of screwness in the dislocation as well as the inherent structure is liked, and this is what we mean by hard core and soft core. Okay, so, a little bit more about the hard core and the soft core. Now, here again I have drawn the same thing, and here you can see that there are this is right now what I am showing you is the inherent screwness or inherent structure of the BCC. So, when I say clockwise, I am talking only right now only talking about the inherent screwness that we saw, the helical structure that we saw. So, there is a clockwise, all the green ones are clockwise and the white and the maroon ones are anti-clockwise. Now, we also said that a dislocation of the same kind would like to go here. So, a dislocation which is of this type would like to go, if you can see these are the gray regions. So, all these gray regions, this will be the gray regions will be soft core. And the white regions would be hard cores. Now, when we talk about another dislocation of another sign which is anti-clockwise, so this will like to go where you have already inherent structure like this, and therefore, it will like to go into the white region is soft core. And gray region is hard core. So, if you have a dislocation like this, you want to sit over here, and from here you would want to jump to here, here and this and this. So, there are 6 different possible directions 1, 2, 3, 4, 5, 6. Okay. But in between all of those you see there is a gray region for this dislocation. So, there is kind of a energy barrier in between the dislocations from movement. So, whether you are talking now, even if you talk about this clockwise dislocation which is over here. So, let us say it is here, this is the soft core for this, and it will want to go here, 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 and there will also be over here. But in between you would see there is a region of hard core for this type of dislocations. Now, when we are looking at it, like I said, this is a 1-1-1 direction, we are looking in the 1-1-1 direction, and over here this is your bar 2-1-1 direction, meaning these planes are your 2-1-1 1-1-2 type of planes, and this is your 0-1 bar 1 direction. So, if we talk about planes, so this is the planes should be oriented like this for one of the, and there are 3 possible planes. So, if we talk about this one, So, let me select another color which will make it easier. So, these are three different (112) planes. All these orange color that you see over here are the 112 planes. What about the 110 planes? The 110, these are the 110 planes. So, as you can see, this is the direction. So, this will be the plane. This is one of the 110 plane, which is 0 bar 1 bar 1, and these are the other three. Now, if you look at the screw dislocation, this one or this one, let us say there is one screw dislocation here, another is here. For them, there are 6 possible directions in 0 1 1, including the positive and negative. Similarly, 6 possible directions in 112 direction, including the positive and negative. So, as such a screw dislocation would like to move. So, screw dislocation will be a long line, and one section, each of this section, if you look at a small section, it has 6 possibilities in 110 directions, 110 planes, and 6 possibilities of 112 planes. So, screw dislocation has 6 possible 110 planes, and I include the negative ones, otherwise you have only 3, and 6 possible and because of this creates, because different sections will want, and the different sections want to move on to different directions. Different directions, planes, basically which plane to select, and this leads to, you can say, pinning and also formation of prismatic loop, which we will show in a moment. But before that, some more properties about the dislocation based on its core structure. We already said that there is no spreading on 110 or 112 plane. What it implies? What it implies? If you remember, in the tau Pn we had something called as tau Pn is, which is the Pearl-Navarro stress. It is proportional to 2g 1 minus nu exp minus 2 pi w, where w was the spreading by b. So, more the spreading, smaller is the stress. If there is no spreading, it implies tau Pn is very large. So, this also implies that screw dislocations are not very mobile. This is coming directly from the Pearl-Navarro stress relation. On the other hand, if you look at non-screw dislocations, they are very mobile, and what will happen is that there are screw dislocations which are not mobile. So, in the process they will, wherever they will leave even a small amount of screw dislocation, it will remain like this, and in the process screw dislocation length will keep on extending, because it cannot move as freely as the non-screw dislocations, and therefore, its length will keep on increasing. And this creates long sections. Now, if you look at a BCC material, if you had to look at the dislocation structure, what you would see is that it is now fully dominated. Even a small amount of after deformation, it is fully dominated by screw dislocations, because the non-screw dislocations are very mobile, they can keep interacting, reacting, and in the process they are stretching the length of screw dislocation. So, everywhere there are screw dislocations. So, the plastic deformation will now be controlled by screw dislocation. Let me add another slide here to draw the diagram that I am trying to explain how this. So, let us say you have a screw dislocation like this. Okay, let me redraw it. So, there is a small section of screw dislocation, let us say this is the edge dislocation part. So, this is along 111. Now, this if this is the 111, this is the screw dislocation, this is the non-screw dislocation. Now, this is mobile, so this can keep moving, and when it moves, what will happen is that this part will become more longer screw dislocation. So, this non-screw dislocation reaches there, this again extends over here, and this comes over here, and this can keep on moving. And in the process, what you see, the non-screw dislocation remains almost same, but this is the screw dislocation and its length has increased. And like we said that these are not very mobile, so they will stick to their place, and in fact you will see them as straight lines many a times. Now, even when they move, they will move, there are many possible directions. So, let us say this is because of their limited motion, they will also generate prismatic loop. So, this is what I am trying to show over here. So, let us say this is the screw dislocation and a part of the edge dislocation over here, another dislocation over here, and then again this is the screw dislocation type. So, this is 111. So, this is the screw dislocation, this is screw dislocation, this is the non-screw dislocation, and this is again non-screw, this is screw, and so let us say that it has moved on to another plane like that. And there is another segment which is in the different plane, I will try to draw it again with another arrow. So, this over here, these are your, now let me, so this is screw, this is screw, this is screw, and if it were there, here is screw, screw. So, this is the screw dislocation, and what we have here, how it is moving is like this. This one is moving in this plane, then it has moved to this plane, and then again it is moving and back to this plane. Over here, this is jumping, then moving here, and then moving here. Now, what will happen next? What would you expect here is something like this. So, this is a non-screw dislocation, this is mobile, this can come here like this can come here, this can keep moving like this can keep moving like this. And after some time, what you may end up with is like this. So, this is here, and the whole screw dislocation is now over here. Okay, it moved, like I said, part of it moved in through one direction, the other part moved through other direction, but eventually they are all on now one plane or along one line. And in the process, these parts which we saw over here, they have now moved together to form a loop, and these are all non screw dislocation, meaning a prismatic loop. So, there have been observations of structures like this, where you see in BCC, particularly tungsten, you would see long screw dislocations, and by side of them you would see prismatic loops. So, this is what we have covered a lot about the dislocations, particularly about the screw dislocation, which make them very different from FCC. So, we will end our study or understanding about dislocations in BCC, and next time when we meet we will start about another system, which is HCP.